So this is one of the most fundamental and basic chapters of class 11th and of mechanics in general, and it's the foundation for a lot of aspects of physics. So make sure we understand all these things properly. So let's begin by understanding the statements of Newton's laws itself, which I'm sure all of you are aware. So there are the three laws given by Newton. So the first law, as you know, is called the law of inertia. So it states that every body possesses a property called inertia, whereby what happens is that any body at rest or in a state of motion has a tendency to continue in its state of rest or uniform motion until and unless there is some external force acting on it. This property is called inertia. Okay. So the definition is itself is quite self-explanatory. Just note it down. We'll discuss with a couple of examples. So this property of inertia can be expressed in in two situations. So for example, if a body is at rest, then to bring it into motion, we must apply some kind of force or impulse on it. Until and unless we apply some force or impulse, it will continue at rest. It will continue at rest forever if we never apply any force on it. So that property is called the inertia of rest. So, for example, we have this situation, let's say, where we have this body which is at rest on a smooth surface. So this is okay. So the body will continue to be at rest unless some external force acts on it. Okay. And the moment the external force acts, it will tend to move. It will tend to So this property is called, this is the inertia of rest. Just make a note of this example. Now likewise, if the same body is already in a state of motion on that smooth surface, so let's say we've given it some push at some point of time. So as a result of that impulse or push given to the body, it's developed some velocity. So it's in a state of motion. So it's having an initial velocity u along this direction. Yeah, we will come to direction of force and all that. When we come to Newton's second law, we'll understand. You want me to scroll up, you mean, Harsh? Okay. Yeah, so Siraj, I think your point is that if the body is lying on the surface like this and we apply a force like this, what will happen, right? This is the question you're asking, Siraj. Okay, so as you know, in that case, nothing will happen. The body will not accelerate because this force will just be absorbed by the ground. The ground will apply a reactionary force which will absorb it. Okay, so that's quite correct. That okay, it will not move towards the right, obviously. If we want to make it move towards the right, then we have to apply a force in this direction. So you're quite right in saying that you know we have to apply the force in the right direction to make it move in the correct direction. Okay. So when I say the moment an external force acts, obviously I mean over here that an horizontal force should act. So I want to make it move horizontally, no? Like that. Is the point clear, Vita? Okay, if two forces are applied from different directions, yeah. So then also see what will happen. The net force. So see, this is what Newton's second law will tell us. That what happens if multiple forces are acting, then we have to calculate the net force acting on it. For example, if two forces are acting equal and opposite, yes, that's why we learned about vectors first. In fact, that's correct, Siddharth. ठीक है? For example, अगर दोनों force 90 degrees पे act कर रहे हैं, so then the net force will be given by that formula square root of a square plus b square. It will be along the diagonal, right? If the forces are acting parallelly, then the net force will become a plus b like that. If they are acting opposite to each other, it will become a minus b like that. Okay, but before we come to Newton's second law, let's understand the second part of the law of inertia. So that is the inertia of motion. So now consider this second situation. So we'll come back to that multiple forces and all that. In fact, most of this chapter is about that only. So this second situation, we have a body in motion. It has a velocity of u along a smooth horizontal surface. Now, this fact that this is smooth now becomes important, okay, because what will happen here is this body will continue with uniform speed, okay, or uniform body velocity, and uniform velocity until and unless external force acts on it. Okay. So this is the inertia of motion. Okay. So for example, if we want the body to slow down, if it's going at u, but we want the body to slow down so that eventually its velocity after some time becomes less than u, then we have to apply the force in this sort of direction. Okay. If we want the body to accelerate, speed up, we want it to accelerate so that after some time its velocity becomes greater than the initial velocity, then we have to apply force in this sort of direction. If we are looking at the same body from the top, and while it was moving like this initially, but we wanted to turn in direction so that after some time its velocity becomes like this, then we have to apply a force in this sort of direction so that it has an acceleration which will make it turn. So later we will learn that this is called centripetal force, which is required for turning the direction of velocity. For all these situations, whether we want to change the magnitude of the velocity by increasing or decreasing it, or we want to change the direction of velocity, some external force is required. Until and unless there's external force, the body will continue to move along the straight line with a uniform speed. So that is the property of inertia of motion. Yeah, so Bhargav, see what's happening in the third case. It may so happen that the magnitude of velocity remains constant. Okay, v is equal to u, so speed is constant, but but velocity is not being equal because direction is changing. Okay, so because the velocity is not constant, the motion is not uniform. Velocity is not equal to u because direction is changing. So the motion is not a uniform motion. Okay, the definition of uniform motion is with uniform velocity. That means the velocity vector should remain constant. Is the point clear, Bhargav? Okay. So this is about the first law. Now let's come to Newton's second law, which is the most important one for us in terms of application. So the second law is also called the force law, because it basically defines the concept of force, the relationship between force and momentum. Okay, okay. So finish up writing this, we'll discuss. So let's come to Newton's second law now. So as I was saying, this is the most important in terms of applications. So the statement of Newton's second law is that the net external force acting on a body, okay, equals to the rate of change of momentum, which can now be written in a single vector equation that the net external force equals to rate of change of momentum. So in this equation, this quantity, it is the net external force, which means that it is equal to the vector sum of all external forces acting on a body. And on the right hand side, it's equals to the rate of change of momentum with respect to time, where momentum is defined as mass into velocity. Just make a note of this, we'll understand. This rate of change concept comes from calculus. As you know, that rate of change of something is basically change in momentum upon change in time, but under the condition that we are talking about a very small change. So this is called instantaneous rate of change. Okay, so now let us look at this more closely. So what this exactly means, that if on a body there are multiple forces acting, like this n forces acting on body, then the net force is nothing but the vector sum of all these. Okay, this is the meaning of net force. Okay, so hope you're done with this. Now, equally important, on the right hand side of the equation, what is this quantity rate of change of momentum? Let us look at this more carefully. The right hand side of the equation, rate of change of momentum. So momentum is defined as mass into velocity, as we just discussed. So if the body is of fixed mass, which is mostly the case, okay, because we are talking about rigid bodies, so they are not variable in mass, okay, then rate of change of momentum will become mass into rate of change of velocity. You're just applying the principles of differentiation. So mass is constant, so it comes outside when you differentiate the product of mass into velocity. So you just apply that principle that the mass is constant. You can just bring it outside, okay, and that becomes mass into acceleration, because this is a kinematics definition that acceleration equals to rate of change of velocity. Therefore, net force equals to rate of change of momentum can imply that net force is equal to mass into acceleration, but this is a conditional statement, okay. This is provided mass is constant, okay. So the general definition of Newton's second law is this one, that rate of change of momentum one, okay, because it applies whether or not mass is constant. But when we are talking about a body of fixed mass, like a rigid body or a particle or something like that, something whose mass is not changing with time, then we can write it as a more specific equation, that net force equals to mass into acceleration. So the common notion of Newton's second law is that F is equal to ma, okay. So most people would interpret, if you ask them what is Newton's second law, they would suggest this, that net force equals to mass into acceleration. But that is actually not the general definition. That is a specific conditional statement, that if we are talking about a body of fixed mass, then the net force is equal to mass into acceleration. So just make a note of this, and we will also discuss the counter logic of this, that what happens if the mass is variable. Okay, so there can be situations where we are talking about variable mass, like a melting block of ice, its mass is decreasing as time is going. Or if you're talking about a very large object like a tanker which is leaking, so mass is decreasing. So in that case, mass is not constant. So we'll discuss what to do in that situation. But provided mass is constant, the statement becomes F is equal to ma, net force is equal to mass into acceleration. Okay, so in this particular chapter, we will be discussing only this situation where mass is constant. However, just as a sort of general knowledge and as a precursor to a future chapter, we will understand that if mass is variable, then rate of change of momentum, when we calculate this, we have to apply what is called the product rule of differentiation, the UV rule that you know. So it becomes rate of change of first quantity into second plus first quantity into rate of change of second. So the net force, which is equal to rate of change of momentum, becomes dm by dt, or the rate of change of mass into velocity plus mass into acceleration. This is for a variable mass system. Okay. For example, a melting block of ice or a tank with a leak. Okay. Or a rocket. Okay. So rocket is constantly losing mass because it ejects burning fuel at a very fast rate. So variable mass systems we'll be studying in a later chapter. The chapter is called System of Particles. Okay, this will come later in class 11. Okay. So, whereas in Newton's laws of motion, we'll mostly be dealing with rigid bodies or constant mass. Yeah, in the second step, what we've done here is, see, we are applying this principle. Differentiation of the product of two things. Now, it is differentiation of first into second plus first into differentiation of second. Remember this, you must have learned in differentiation. Have you learned this principle in differentiation yet? Okay, so that only we are applying. Okay, so differentiation of mass into velocity. Okay. Mass is the first quantity, velocity is the second quantity. So just apply that UV principle. Yeah. Okay. So you can also see in this equation, if you just put mass as constant, it reduces to the first one, because if mass is constant, then this term will become zero. Dm by dt will be zero. So you can always think of the constant mass case as a special case of this one. This is the more general equation. This will apply whether or not mass is constant. But if mass is constant, this first term just becomes zero. So you're left with F is equal to ma. Net force is mass into acceleration. Okay, so let's look at a couple of examples of application of this. Okay. So let's see a situation like this. What we have is, so this is a block of certain mass. Now what is happening is that so two people are applying forces. So two people A and B over here keep a block of mass, let us say 100 kilograms, at rest, suspended by ropes as shown. Okay, so if theta is equal to 37 degrees, okay, find the force or the forces FA and FB applied by A and B on the ropes to keep the block at rest. Okay. So let us see how we will apply Newton's second law in this. Just make this diagram first or note down this situation. And so on the block there are two hooks, let's say like this, and these are the ropes. So by pulling on the ropes with certain force, they are keeping the block at rest. Okay. So let's understand what we'll do here. So first of all, we have to figure out that the momentum of the block is zero because the block is at rest and it continues in a state of rest. Okay. So that means the rate of change of momentum, which is the net force acting on it, should be zero. So for the block to continue in a state of rest, okay, and this is called equilibrium. It should be in equilibrium. Okay, so the definition of equilibrium is that net force is equal to zero. Okay, not written down the question. Okay, okay, no problem. Finish writing down the question first. Okay, so let's come back to this. So the momentum of the block has to remain zero. It has to remain at rest. So that means what is happening? The net force acting on the block is zero. So let us see what all forces are acting on the block. Okay. So obviously it is vertically suspended. That means the earth, as you know, is applying the gravitational pull on it. So there is mg which is acting vertically down. So मुझे पता है कि if there was no other force holding the block, then it would be in free fall. Na? It would fall down with an acceleration of g, like the vertical motion situation that you know, free fall of an object. So to prevent it from going into free fall, what I'm doing is I'm applying force through the rope. So one guy is applying force to the rope like this, the other guy is applying force to the rope like this. So these are the forces which are acting. Fa, let's say this is the force applied by this guy. Fb is the force applied by the person B through the rope. And these forces are acting at an angle of theta equal to 37 degrees each. Okay. So the net force equals to 0 here means that the vector sum of Fa, Fb and Mg written as a vector should be 0. Okay. So now there's a number of ways in which we can solve this, including component algebra. Okay. Or we can use triangle law, whatever we want. Okay. A number of ways of solving this. We can take this as x and y, and we can understand that Mg is like this, Fb is like this, Fa is like this. Okay. So theta is 37. So if we break this into components, we can see that this component will be 4 by 5 Fb. This component will be 4 by 5 Fa, because we know that cos 37 is 4 by 5. Okay. And this component will be 3 by 5 Fb, and this component will be 3 by 5 Fa. So immediately we can see that Fa must be equal to Fb. Okay, because along the x-axis they should cancel, and 3 by 5 Fa plus Fb must be equal to Mg. Okay, so 6 by 5 Fa, which is equal to 100 into G, so 1000 newtons. So Fa should be equal to 5000 by 6, which is 2500 by 3. So that means the magnitude of force applied by each of them is equal to this much. Okay. Because we are taking G as 10. Okay, so yeah, what we've done, Harsh, in this is that we have applied the condition for the vector sum of the three forces to be zero. The block is at rest, so the weight of the block mg is balanced by the vector sum of fa and fb. So in this diagram, we have broken fa and fb into components, and we've equated the sum of the y components, that is 3 by 5 fa plus fb, to balance the downward mg, and the horizontal components are cancelling each other, so fa is equal to fb. Okay, and that's how we have done the calculation for. Yes, horizontal forces should cancel, so along the x-axis the net force should be 0. So 4 by 5 fb should balance 4 by 5 fa. So that is what is giving me this equation. Okay, this is horizontal components cancel, that is this. And the second equation is coming from vertical components cancel mg, which is acting downwards. Right, so Harsh and Bhargav, this is clear, I hope. Okay, let's move on to another example. Okay, in our next example, what is happening is that we have a block on a smooth horizontal surface. Block of mass m equal to 10 kg at rest initially on a smooth horizontal surface. So at t equal to 0 initially, this block is at rest. Okay. Now from t equal to 0 onwards, a constant horizontal force F acts on it, where the magnitude of this force is 20 newtons. This kind of force acts on it continuously. Okay, so we want to find the acceleration of the block. Secondly, its velocity at t equal to 2 seconds. Third, the displacement of the block from 0 to 5 seconds. What is the displacement? We want to find this out. Okay. So work this out quickly. This is a very simple application of this Newton's second law. You apply net force is equal to mass into acceleration, and then you use kinematics. Okay, so hope you have worked this out by now. How much is the acceleration coming out to be? You can see the net force on the block is 20 newtons. Okay, so the acceleration should be 20 newtons divided by 10 kilograms. So that is 2 meters per second square. So initial velocity is 0, acceleration is 2 meters per second square. So velocity as a function of time should become like this. So from this you should get the velocity as 4 meters per second at t equal to 2 seconds. And you should get the displacement. So 25 meters at t equal to 5 seconds. So hope this is clear, everyone. Let's move on to the next question. So now in the next example, what is happening is you again have that similar situation, that on a smooth horizontal surface you have an object which is at rest. So imagine this is the surface of a table or something which has a smooth top, and on this now we have kept a block like this initially at rest. Now this block is acted upon by two forces simultaneously, like this, F1 and F2. So a block of mass 10 kg again is at rest initially on a smooth horizontal surface, and from t equal to 0, two horizontal forces F1 and F2 start acting on it continuously, such that magnitude of F1 is equal to magnitude of F2 is equal to 20 newtons. Okay. And the angle between them is 60 degrees. So in the diagram, this angle is 60 degrees. Okay. So again, we want to find the block's acceleration and displacement after 2 seconds. Just work this out quickly, people. Yeah, Deep, you have calculated the net force. Now you have to divide it by the mass also. So just divide by 10, then your answers are correct. Okay. So here we have to understand it like this, that if you look at the top view, then on that block, there's a combination of the two forces acting. Which are of same magnitude, but at an angle of theta. Okay. So F1's magnitude is equal to F2, which is 20 newtons. Okay, and theta is equal to 60 degrees. So you can see that the net force will be like this. This will be the net force. Okay, it will be the vector sum of these two. So we can use that theorem. 20 root 3 newtons will be the magnitude of the net force. Okay. So here I am using this theorem that if I have the sum of two vectors whose magnitudes are same, then the resultant like this, using this theorem, that if mod A is equal to mod B is equal to A, let us say, then A plus B has a magnitude of 2A cos theta by 2. Okay. This is the rhombus theorem. So you can use that, or you can still use the parallelogram law or component algebra, whatever you like, but vector sum will come out to be this much. So acceleration will have a magnitude of net force divided by mass. Okay, so the body will accelerate along this direction only, along the net forces direction, and that will be 20 root 3 newtons divided by 10 kg. So this is the answer to the first part. And then the displacement you can just find by the formula, okay, because initial velocity was 0. Okay, so let us continue ahead. So hope this calculation was clear to all of you. Now next, we'll look at Newton's third law. Complete this series of laws. This is called the action-reaction principle. So the statement of the law is that every action has an equal and opposite reaction. And I'm sure all of you have experimented with this principle and realized the painful truth about it. Okay, that if you hit someone or something very sharply with your hand experiences an equal and opposite force, which can cause injury or at least pain. Okay, so it's a common everyday experience. But let us understand this in more technical language. So basically, what this means is that if a body, let's say A, applies a force on another body, let's say B. So this is, let's say, the action, and we can denote it as FBA. Okay, so this is the force on B by A. Then the body B must apply an equal and opposite force on A. So this one is the reaction, is it? Which will denote by FAB. Okay, that is the force on A applied by B. Okay, so equal and opposite means that the force on A applied by B is minus of the force on B applied by E. They are equal in magnitude and opposite in direction. So write down the principle first, then we'll understand this with examples. Yes, so this is because of the interaction of you know particles of physics through the fundamental type of forces. So what we'll understand is, whether we are talking about gravitational force or we are talking about electrostatic force. So in gravitation, if we have two particles of mass m1 and m2 at a distance r, they apply equal and opposite forces on each other. So two particles or bodies of mass m1 and m2, they apply equal and opposite attraction force, which is the gravitational force F, where you know that F is proportional to the product of the masses and inversely proportional to square of distance. Or another example of the same thing is in case of electrostatic force. If you have, for example, two positively charged particles, plus q1 and plus q2, at a distance r, they repel each other with equal and opposite force. So you can see these are the two of the fundamental forces known in physics. Okay? And they exhibit the property of Newton's third law, the action reaction principle. Here also the force's magnitude is proportional to the product of charges divided by r square. Or in the case of opposite charges, if one charge is positive and the other is negative, they apply attractive force on each other, but they are also equal and opposite. So in the case of electrostatic force, whether we are talking about attractive force or repulsive force, it's the same principle, action reaction. Now, as a rule, we don't know that much in detail about nuclear forces and what is called the weak forces, the forces that act between the subnuclear particles. Okay, but whatever we see in the macroscopic world around us, including atomic physics, okay, um, is mostly consisting of the combination of electromagnetic forces and gravitational force. And these forces follow the principle of Newton's third law, which is why in mechanics, in classical mechanics, all our mechanical systems are in line with Newton's third law, that every action has an equal and opposite reaction. Okay, now let us understand Newton's third law in another context. Okay, if you look at a mechanical system as opposed to fundamental particle level, what is happening? So, for example, we have something like this. We have a spring attached to a wall like this. It's a spring. Now, next up, what happens is, let's say, an external agent in the form of a person actually pulls the spring, thereby stretching it. So, in this case, in order to stretch the spring in length, you will have to apply a force to this end of the spring in this sort of direction. This person applies a force like this. Okay. The spring will apply an equal and opposite force, which we can call the spring force like this. So, an external agent applies a force F, okay, which we can call the action to stretch the spring. The spring will apply an equal and opposite reaction force on it. On the external agent. So as you can see in the diagram, that spring force is acting in such a way that the magnitude of the spring force is the same as F, but the direction of the spring force is opposite to the direction of the force. So every action has an equal and opposite reaction. Okay, so hope this is clear. Okay, so with this, we more or less come to a conclusion of the first lecture of Newton's laws. Okay, but before we finish up, we will see few concepts from vectors which are very necessary. Okay, so next time we will be looking at applications of Newton's second law, that is net force is equal to mass into acceleration. So during this, the calculation of net force as the vector sum of various forces. So mostly you need to be clear about component algebra of vectors. That includes resolution of a vector into components, okay, and addition of vectors by component algebra. So make sure you revise these couple of things. Okay. So as a quick recap, how do we resolve a vector into components? If with respect to our x and y axis, a vector is drawn such that it makes an angle theta with the x axis, then as you know, the x component of the vector becomes a cos theta, and the y component of the vector becomes a sin theta. So this becomes important. No, I will be send. Yeah, you can start solving for module, but I will be sending you a worksheet also. So first do that. Plus, I'm giving you some instructions on what to do as homework for this lecture. Okay. So first of all, you do a bit of revision of vectors if required, especially if you're not that confident with components and resolution. So make sure you do this revision of vectors. Now the next thing, you will also be using some reference books for this chapter, Newton's laws of motion. So we will be using concepts of physics, okay, part 1 by Dr. H.C. Verma. This is Bharati Bhavan Publications. So mostly we'll be using this for problems and examples. We'll be also using the iit hub module for both theory and problems. Okay. So these you will be consulting immediately right now. Okay. Now for additional theory reading, you can also consult this book. This is for additional theory reading. Okay, so this is optional, and you can also do. Okay, so this is also optional. This is Arihant publication. So you can get hold of all this material. But for the moment, yeah. So as I said, these HC Verma is compulsory for you right now because we will be doing problems and examples directly from that. These two books are optional. Okay, the third and fourth, they are optional, but HC Verma you should have because we will be discussing in class also problems based on that. And of course, the IITN's Hub module you already have. Okay, so for next time, read about Newton's laws, okay, the three laws, then something called free body diagram, and something called normal reaction force from either module or HC Verma or Resnick-Halliday, whichever is preferable to you and whichever you have access to. Read this. Apart from that, I'll be sending you worksheets also, so don't worry about the homework part. And after the second lecture also, you can start working out questions from both HC Verma and module. I will tell you which questions to attempt also. Okay. So that's it for today's session, people. Wish you all the best.